Hi folks, it's Professor Elliott, and this lesson is on active filters and is in lieu of the class I had to cancel today. My apologies for that. I'm feeling somewhat better, but anyway, hopefully another day or two be back to normal. So anyway, I hope this video you'll find to be easy to follow and satisfactory, I hope. So we're going to look at the low pass, the high pass, the band pass, and the notch filter. Okay, so anyway, let's continue on. All right. So the low pass filter, it is used to pass all signal frequencies below critical frequency FC. So FC is the critical signal frequency, and the low pass filter will pass all frequencies up to FC and then roll off after that. Okay, so we can say then that frequencies higher than FC are attenuated. And we'll look at that when we get to the graph. Okay? All right. So that's what a low pass filter is. So this is the basic low pass filter. The filters we're going to be working with are called active filters because it uses an op amp, and we'll talk about that. But the basic filter is composed of a series resistor and a parallel capacitor, and this should be V out. Okay, and the operation is really easy to visualize. Recall from your first and second semester that the capacitive reactance is given by this formula. And you can see then that if you increase the signal frequency, then the reactance then decreases. So you could easily imagine, for a given value of capacitor, a frequency where XC is effectively 0. So what's going to happen is that the frequencies that are below FC, the reactance on the capacitor is high enough not to really affect them. So the frequencies will simply just pass through the filter, and at higher frequencies they are simply shunted to ground by the low capacitive reactance. All right, so make some notes. So we say all frequencies below FC, and I'll show you how to calculate that in a minute. Pass through the filter at higher frequencies. I mean, it's all relative, so I mean, the low pass filter, you could be filtering in the hundreds of hertz or in the megahertz. It's high and low is all relative, but for a given application, we say then that at high frequencies, signal frequencies, maybe is better. Signal frequencies. Capacitive reactance FC is sufficiently low enough to shunt them together. So again, it's all hinges on the reactance of the capacitor. When the capacitor reactance is high, the signals pass through the filter. When the reactance is low at the higher frequencies, then those high frequencies are simply dumped to ground and are attenuated. Okay, so those two components is actually what's doing the filtering. The formula for calculating FC is simply 1 divided by 2 pi FC. So if we let I meant R. So let's let C equal to be 0.01 microfarad, and let's let R equal to be 5.1 k ohms. Therefore, FC two pi times don't forget to enter the value is micro, it was 10 to the minus 6 in your calculator, and I just work out that. I get, if I just round this off, 3.12 kilohertz. So you can see then just by playing with the values of the capacitor and the resistor, then you can set FC to whatever value you need to be. Okay. All right. Hertz. Yeah. So this is the basic graph of the low pass filter, and you can see then it's passing all frequencies. So we have frequency along the horizontal, and gain normally expressed in dB on the vertical, and pass all frequencies up until FC. So if we just stick with our number there that we used, we had 3.12. Okay, and the pass band, or the bandwidth, is the range of frequencies it will pass. This line here, this is the roll off, and for a single resistor and capacitor in the filter, this is going to roll off at a rate of 20 dB per decade. And all that means is that for after FC, if you increase the frequency by a factor of 10, then the gain will drop by 20 dB. If you increase it by another factor of 10, another 20 dB, and so on all the way down. Again, for a single resistor capacitor filter, then at this point here, this is at 1,000 times FC, and this point right here, okay, for the gain, this would be down at minus 60 dB. All right, so whatever the gain, we're going to do an example, but whatever the gain is in the passband, it will be 60 dB less than that when the frequency is at 1,000 FC. This 3 dB point is basically saying that at the critical frequency FC, which is just touches the line right there, then the gain is down 3 dB from that point. So we'll bring that out in our next example, but that's what that means. All right, so anyway, so that's the basic response curve. So let's then turn that into full-blown, this would be called the active low-pass filter. And if you look at the laboratory circuit, you'll find I'm using a different set of numbers, but it's the same circuit. So anyway, that's going to be the output. I'm trying not to talk too loud or I'll start coughing, so thanks for your understanding on that. Negative, positive, Vn, okay, this would be C, and this would be R. Okay, so again, I just draw a little line here. So this bit here is the actual filter. This bit here is providing the voltage gain, and this is simply the non-inverting amplifier. Okay, so we're doing a little example here. So let's let this equal to be 75K. Let that be 68K, and we'll just stick with the. Let's change this to 10K ohms, and we'll leave this at the. All right, so let's just go ahead and and calculate out the critical frequency, the output voltage. So let's let V in be 300 millivolts, and we won't worry about if I mean RMS or peak or whatever. You can easily handle that, but just say it's 300 millivolts. Okay, so I'm just going to just write this down. Okay, so we got 10K, 0.1 microfarad, 75K, and 6.8K. Okay, so the advantage of using the op-amp, as we know, the input impedance is essentially infinite. So the op-amp draws, practically no current, so it doesn't load down the filter. And this is a really great advantage because if you were trying to drive, the next circuit stage with the filter directly, its characteristics would load it down. So the op-amp essentially makes the filter behave more ideal. So that's a good situation. Let's go ahead and we'll just solve this. It's quite straightforward. Just solve, determined by R and C. So the first thing we want to solve is for the critical frequency. Alright, so 10 times 6. Alright, so that's 1.59. We'll leave it like that. That should be fine. Kilohertz. Okay, and again, that the voltage gain. Just the standard non-inverting amplifier. So we have 75 divided by 6.8 plus 1 equals 12.03, and then convert that into dB. It's just 20 log. Alright, so AV equals 12 equals 21.6 dB, okay? Right, so that's the gain. And once we know that, then we can calculate the 0.59, the output voltage. So this is the output voltage, and let's call that PB. So that's the output voltage in the passband. So that's going to be equal to Vn times the voltage gain, just voltage gain. So that's going to be 300 millivolts. And this will use the gain as a ratio, not as the dB. So 0.3 times 12.03 equals 3.61 volts. Okay, so let's now write it down. 3. To a little graph. Frequency. Like that. Okay, so this would be then FC, so which I think was 1 point. Okay, and again, this is going to be the pass band, or the bandwidth means the same thing, like that. So it's going to pass all frequencies up to 1.59 kilohertz, and then roll off at minus 20 dB per decade. Now you can get, by using more resistors and capacitors, you can increase that roll-off rate. You can make it 40, 60, 80, 120, and all that does, it just makes it makes this corner sharper, and it makes it roll off quicker. So it just depends on how sharp you want the frequencies beyond FC to roll off. I mean, ideally, you want the response to be like that. Or at FC, it would just, the signal strength would just, it would just drop right off. It would block everything perfectly, but because they're real components, they have this corner here. So anyway, for our purposes, it's just 20 dB per decade, but that can be made much higher just by changing the design, sadly. But anyway, we're not going to worry about that. Okay, so so let me extend this line. It's supposed to line up with that. Okay, so we determined that the output voltage in the pass band was, next one, 3.61 volts. Okay, and then you can see as you get near the curve here, it's going to start to drop off. Okay, now at FC, and this is an important point, at FC, the output voltage is equal to 70.7% of whatever the output voltage is in the pass band. So if the output voltage is 3.61, experimentally, you're at the critical frequency when that voltage has dropped to 2.55 volts, right? So you just monitor the output. When it's down 2.55 volts, boom, you're at FC. In the lab experiments, I think the passband gain is voltage is 5, right? So if you take the 5 times the 0.707, that's 3.5. You can easily, then when your output voltage is at FC, then it's 3.5 volts, and you're at the critical frequency. So it's very easy to experimentally determine that. this point here, and I mentioned that briefly also, is the minus 3 dB point. So at FC, so we say at FC, the decibel voltage gain is 3 dB lower than in the pass band, and VO is reduced by 0.707 in the output in the pass band. All right, so I'm going to have to just pause this for a while. My pen is flashing red, so anyway, I'm going to let this charge, then we'll just continue on. Okay, but you won't know the difference. Okay. All right, let's see if this is charged up enough to continue on. I had done a video yesterday for the first semesters, and I guess I forgot to charge my pen. Anyway, where were we? Oh yeah, so we were talking about the at FC, how the gain is down 3 dB. So we had calculated earlier that our gain in the pass band was 20.6 dB, and for a single filter with one resistor and capacitor, this is at 1000 FC. So if you take your 21.6 minus 60, that would mean then that at 1000 FC, the gain is down to minus 38.4 dB, or a change of minus 60. So in the pass band, the gain is 21.6. At 1000 FC, it's down to minus 38.4, so it's well attenuated. The output voltage at FC is 2.55, which is 70.7% of the 3.61, which is what it is in the pass band. So, okay, let's go on. High pass filter. So this is really the opposite response as for the low pass. So it will basically pass all frequencies beyond critical frequency FC, all lower frequencies are effectively attenuated. Okay, again, so this is the basic filter. Again, that should be the output of the filter. Notice that the position of the capacitor and the resistor are interchanged. Again, the operation is all really just contingent upon understanding how the reactance X of C changes with the frequency. So again, as you know, the formula for x of c is 1 divided by 2 pi fc. So if we raise the signal frequency, the reactance goes down. So basically then at lower frequencies, the reactance is sufficiently high as to effectively attenuate or block the signal from reaching the output. And at higher frequencies, the reactance is low enough, it passes it basically straight through. Okay, so we can say then for frequencies less than FC, XC is sufficiently large enough to block the signal from reaching the out at higher frequencies. The low reactance passes the signal to the output. And again, the formula is the same formula for the critical frequency, 1 divided by 2 pi RC. All right, so if this was an ideal high pass response, then basically then it would pass all frequencies beyond FC, right? And then these would all be blocked due to the high capacitive reactance. But because, again, we're dealing with an imperfect real-world device, the response looks like this. Okay. So at frequencies below FC, this is going to roll off at minus 20 dB per decade. Again, higher roll-off rates are possible, which would make that corner, you can make it, more roll-off at a much sharper rate. But anyway, for the standard 20 dB per decade roll-off, then the frequency here would be 0.001. So it'd be 1/1000th of FC, as opposed to the low pass filter, it would be 1,000 times FC. So it's just sort of the opposite. And the gain is down 60 dB from whatever the gain was in the passband. Okay, so anyway, let's go and do an example, if that's okay. So we're going to have the input signal V in, and this will be resistor R, and this will be capacitor C. Again, just our non-inverting amplifier. So let's let that be 100. Let that be 10. And let that be okay, so that would be 0.01, 25K, 100K, 10K, and let's let that equal to be 500. Okay, so let's go and work this part here. This part here is the filter, and this part here is providing us the voltage gain. That out. Okay, so 1, the critical frequency FC goes 1 divided by 2 pi RC, and just again, and so that's going to be 1 divided by 2 pi times 25 k ohms. So in my calculator, okay, so that's 636.62 hertz. So just for the sake of this example, let's just make it 637, okay? Okay. All right. So then 2, what is the voltage gain AV in the pass band? AV equals RF RI equals 100K equals 10K equals 11. So the voltage gain dB equals 20 times a log of AV equals 20. So that's going to be 20 times the log of 11, be 20.83 dB. All right. And the output voltage in the pass band equals Vn times AV 500 millivolts times 11. Use the ratio, not the dB. 0.5 times 11 equals 5.5 volts. Okay, so frequency AV/dB. All right, so this would be like that. Okay, so this was FC, was 637 hertz. Okay, so this is the pass band. So this is the output voltage in the pass band. Is 5.5 volts. By the way, this doesn't continue on indefinitely. The upper limit of the frequency limit of the filter is the maximum frequency of the op amp, which for a 741 it's either a megahertz or 1.5 megahertz. I can't remember, but it doesn't go on indefinitely. And eventually, if you kept increasing the frequency, it would just roll off anyway. But so this is the upper frequency limit of whatever op amp you're using. Okay, so anyway, I extend this across to there. Okay, so that was 20.6 20.83 dB. So that means then from here to there, okay, it's minus 60 dB. So this is at minus 39.17 dB, and this is at 1/1000th of FC. The gain is now minus 39.17 dB, so it's attenuated. But it's 60 dB down from the passband gain of the 20.8. This point right here. Okay, so this is, this is the minus, what's going on there? Minus 3 dB. So that means then at FC, which is right there, the gain is 20.83 minus 3, so 17.83 decibels. And also at FC, VO equals 0.707 So 70.7% of the passband voltage. So that would be then 3.89 volts. So summarize, in the passband, the output voltage is 5.5. At FC, the output voltage is 3.89. The gain is down to 17.83 dB, which is, and at FC, that 3 dB point, that's a constant point. So at FC, the gain is always down 3 dB. All right, so that's the high pass filter. Okay, the band pass. So the band pass is really just a combination of a low pass and a high pass filter. It makes no difference which order you cascade them in. So if you fed your input signal V in through a low pass filter and then through a high pass filter, you get the band pass response. Or you feed it to the high pass first, then the low pass, and you get the band pass response. Okay. All right. So, yeah. I went too far. So that's the standard band pass response. So you can see then it's passing in the bandwidth of the pass band is passing a range of frequencies that are between FC1, which is the lower critical frequency, and FC2, which is the upper critical frequency. This response here, this is the high pass response. And here, this is the low pass. So this is the response. That's the low pass, and that's the high pass. At FC1, the gain is down 3 dB from the passband gain, and at FC2, it's down 3 dB from the passband gain. When you do this in the lab, okay, the instructions will start you off somewhere like in the middle here, and as you increase the frequency, like that, the voltage is going to be constant, right? When it starts to drop off, right, when it reaches your 70% point, you know you're at FC2. If you bring back the frequency, it'll come all the way back up, keep lowering it, it'll then drop down to FC1, so you can easily experimentally determine these 2 points. That center frequency FO, that's like the geometric mean, the center of that waveform shape. So anyway, let's just make a couple notes here. Okay, so FC1 is the lower critical frequency. FC2 is the upper critical frequency. FO is the center frequency, which is given by, okay, so it's not quite in the center, okay, so that exactly is given by that formula. Okay, so anyway, so let's just, by way of example here, if I can, let's let FC1 equal to be 5 kilohertz, and let FC2 to be 8 kilohertz, and let's just graph that, okay? That 5 and 8, yeah. And you can see exactly where those frequencies fall. All right, so anyway, this is going to be like this. It's going to something like that. Okay, FC2. Make sure. Okay, so oops. That's going to be the bandwidth. Okay, and then the center frequency FO. We're going to calculate that. Okay. All right. So let's go and calculate the numbers. And we'll 6.32 kilohertz, and this would be okay. All right. So that, you can see that, and a measure of, you know, I mean, if you move, you know, the FC2 that way and FC1 that way, you can make the, you know, the response very narrow or very wide depending on how many frequencies you want to, you want to pass. You want to pass at just a small, maybe one frequency, or a very whole wide range. So the ones that pass a very wide range of frequencies are less selective than the ones who are just targeting one or more frequencies. Okay, so that's really all that is. Again, at FC1, FC2, right? The gain is going to be down 3 dB from whatever the pass band voltage gain happened to be. Okay, so if the gain in the pass band was 10 dB, then this would be 7 dB. Okay, and again, we could say the FC2 is at 8, the bandwidth is at 3, so we move that way, so the bandwidth is going to increase. Back and stick them on the graph. Okay, so 1, so the bandwidth is simply the difference in frequencies between FC1 and FC2. All right. The center frequency is the square root okay, so all right, so okay, so this would be, and then 3, just the in here, the Q is the quality factor. So the quality factor, which is just sort of a measure of filter selectivity is then AC back, and that's given by the equation Q equals FO. Okay, so it's just a ratio. So this is 6.32, and the bandwidth is 5. So this is 1.26, and also that we change it that much to 1.26. Okay, so basically, as you make this number here, the bandwidth, as that is made larger, the Q is going to become smaller, right? We can say that at FC1 or FC2, output voltage VO is 0.707 of the times the output voltage in the passband. And we could also say then that at FC1 or FC2, the gain is reduced by 3 dB. Okay, so let's just kind of resketch that again. Okay, so let's assume that the passband gain is 30 dB, and let's assume that the passband voltage is 4 volts. I'm just going to write this down myself. Okay, so let's then leave FC1 at 5 kilohertz, and let's change then FC2 to 12 kilohertz, and let's see what effect that has. Okay, so 1, the bandwidth equals upper critical frequency minus lower critical frequency. Okay, so we moved FC2 up from 8 kilohertz to 12, so the bandwidth increased to 7 kilohertz. 2, the center frequency, FO, again is the square root of FC1 times FC2. Okay, because both frequencies are in kilohertz, you can just drop the units because the answer is going to be in kilohertz. So it's basically the square root of 12 times 5. So that's going to be 7.75 kilohertz. 7.75. All right. Anyway, that's 3. The quality factor equals FO divided by the bandwidth. So that's 7.75 divided by 7. Oops. Answer K equals 1.11. Okay. So basically, as you make the filter less selective, the quality factor, the number then goes up. So as you move FC2 out, then it passes a wider range of frequencies, and the filter is said to become less selective. Okay, so compare that to, it's just one way to kind of measure the selectivity of a filter. I might do one more example too, and just really push that out. You can see how that changes. And the last thing for this one before we graph it was I'd given us the pass band voltage gain. That was just a given number. Excuse me. So therefore, at FC1 and FC2, AV is going to be down 3 dB, so it's going to be down to 27 dB, and likewise at FC1 and FC2, VO equals 70% of the 4-volt output in the passband, and that would be equal to 2.83. Okay, so it's very easy. Sketch it like this. Okay. FC2. Okay. FO was, I think that was 7.75. Okay, so the bandwidth (7 kilohertz), and I set the pass band voltage was 4 volts. And I said that we just assumed as a given value that the gain was 30 dB. Therefore, at FC1 and FC2, the gain is down 3 dB or 27 dB. Okay, and then at FC, the output voltage was 70% of the 4 volts, which we calculated to be 2.83 volts there. Okay, so to determine then, the voltage here is 4. When you decrease the frequency, it falls to 2.8. You're at FC1. Bring the frequency back up, goes back to 4 volts, increase it, falls to 2.8, you're at FC2. So it's very easy to determine that. So just one more. We won't sketch this one, but just throw some numbers. Okay, so let's leave FC1. And let's push that out in fairways. Okay, so the bandwidth. Okay. The center frequency. Again, you don't have to put the kilohertz in the calculation. Just do 5 times 30 square root. You're going to get your answer in kilohertz anyway. Okay, so basically the square root of 150 goes 12.25. And then the quality factor and then that was 489. So you can see then that as we keep making the increasing the bandwidth, then the quality factor number goes down, and it becomes less selective. Well, let's do one more. Why not? I have time, as long as my throat holds out. So I'm having to talk a little bit soft. I hope it's picking it up okay, because I will definitely start coughing if I talk too loud. So let's leave that there, and let's push that out. Okay, and then we calculate the bandwidth. Center frequency. And the quality factor, again, is going to be that. See, and this number keeps getting smaller. Okay. Oh, let's do one more. And then we're going to move on to our final filter. Okay. So with this one here, relatively speaking, this has become much narrower. Okay. bandwidth then would be simply 2 kilohertz, the 7 minus the 5, right? The center frequency square root right, so that would be the square root of 35, 5.91 kilohertz, and then the quality factor again would be the 5.91 divided by the 2.96. So I brought FC down, so it made this part here narrower, and then notice that number went up. So the higher the Q, the more selective the filter is, and the lower the Q, the wider the bandwidth, the less selective it is. All right. Oops. Okay. The notch filter is essentially the opposite of the bandpass filter. So this is sometimes called band reject filter. And the basic idea is to take the bandpass filter and then you feed it into an amplifier with the gain less than 1. Look in the lab experiment, okay, and you'll see the output is an inverting amplifier with the gain less than 1. You can calculate that out easily, and that gives you the notch filter response. So this is basically, if you just imagine the bandpass response mirrored over, this is what you got. And you can see then the notch filter, it's used to take out a particular frequency or a range of frequencies. It notches them out. The bandpass, the pass band is going to be from 0 and all the way up to FC1, and then again from FC2 all the way up to the upper bandwidth limit of the amplifier. Okay, the formulas for the bandwidth, the center frequency, and the Q are all exactly the same as the bandpass. And so when you're doing this in the lab, then the instructions will have you starting off like somewhere here, and then you're going to move over like this, okay, and then you're going to see the voltage is going to drop, okay, and so as always, when it reaches FC1, VO equals, it's reduced by 70%. Of whatever the voltage here is in the passband. Anyway, and then you're going to keep increasing the frequency, and then you're going to see the gain, the output voltage go all the way down. Okay, and then you keep going. You'll see there's that bottom there. The middle of that bottom is where FO is. Then you're going to increase it, right? The frequency, the gain comes up and up and up. Again, when it reaches the output voltage, again is 70.7 of the passband voltage. Your FC2, increase a little more, then you're back up to your passband voltage. So I'd recommend in the lab either sketch this out in front of you or just have it in your head, and you're kind of like rolling a marble, or a ball, down a track, so you can kind of visualize, where you are as you're moving the frequency up and moving up and forward and back along that curve, and Anyway, so my throat's kind of done, and I'm pretty much done anyway. So anyway, I hope this was useful for you. I'm sorry for canceling a lecture today, but um, it wouldn't have been good. Anyway, we'll hopefully catch up with you on Friday. All right, thanks, and have a good night. All right, thanks, bye.